Good. How was your education so far? Yeah. Good. Sounds like an approval. Right. The format for this is just going to be, I'm going to give you probably an hour-ish about what it is, and then have a bit of a break. Then I'm going to come back and maybe do a bit of demo, bit of interactive demo maybe, and some Q&A. Yeah. So don't expect too much interaction for the next hour. Right. So thus far, I guess you've probably been pretty focused on underlying concepts, blockchain, Polkadot, pallets, smart contracts. This is a different blockchain. And it's intended to be backward compatible. Unlike with Polkadot, we really went back to square one and took a really quite idealistic approach with how this protocol is going to work. And I started by writing the spec rather than writing the implementation, which is what we did with Polkadot. So in this sense, it was a little bit more back to the philosopher attitude rather than the engineer attitude that could perhaps be said to characterize early Ethereum development. In order to get the expertise behind this specification seeded in the world rather than in parity, we made a prize. You might have heard of it, the Jam Prize. This is a big prize fund for those teams, those people interested in implementing this specification. And in order to help us develop the thing, to work on real-world hardware, we bought ourselves some real-world hardware. So that's what the grey paper looks like. It's actually got quite a lot of English in, but it is a formal description. There's maths. It's all based on pretty standard set theory with some funky notation because it reads a lot easier if certain shorthands are in place. But if you understand set theory, it won't be too foreign to you. And similarly, it's actually, I wrote it so that if you're familiar with the yellow paper, Ethereum's formal specification, it wouldn't be too big of a jump. As I said, big prize pool. And there are a number of teams actually busy implementing this. So anyone here who is actually a member of a team? Yeah, 1, 2, very good. And the idea is with the prize that there's actually a few different milestones. So it's not just like, all or nothing. First and second milestones shouldn't be desperately hard to make work in pretty much any language. And then after that, it's really about making it go fast. Performance is important. And we are keen on there being a large number of implementation languages. This is less about sort of being practical and more about desiring a well-seeded bed of expertise within the world. And the more different languages, the sort of broader the set of minds that understand the protocol. I think at the moment it's 42, not sure, 42 I think last I checked, independent teams declared themselves as implementing it. And I think there's probably about 15-ish of them that actually can import blocks now at various speeds. Some fast, some not so fast. Now the toaster is an interesting one. It's a piece of hardware. I mean, it's a lot of interconnected pieces of hardware. That's one of the racks. There's 10 in total. That together can run a full-scale jam network at full speed, more or less. There's a couple of corners cut on memory bandwidth, if you care. But beyond that, it should be a pretty correct set of hardware for running a full-scale jam network. Why bother? Why not use a test net like we did with Polkadot? Well, because I actually want controlled conditions for testing the protocol and for optimizing it, looking into bugs, looking into performance issues. And this was something that was very much missing with Polkadot, and it led to years of suboptimal performance. So it's one thing we're going to really nip in the bud and get in early. And we're already, there's already a very senior engineer deployed in getting our prototype jam implementation, PokerJam, this Parity's prototype jam implementation, running on this hardware. It's actually only half built. We have half a toaster at the moment. The other half is coming early next year. And indeed, by early next year, it's our expectation that we'll have a reasonably performant implementation on here. And we will have the software to be able to test it under certain conditions, under whatever conditions we want. Dodgy networking, net split, multiple implementations disagreeing with each other, whatever it is. It's a pretty fast computer if you like sort of CPU power. Right, let's get on to the meat. What is jam? There's my little picture of jam that I drew, I don't know, 2 years ago or something now. But it's about right. So it's this sort of flower thing going on, this kind of petal thing going on, right? You've got these petals, you see that? Petals coming out, and then in the middle, we have some sort of core. And then around the petals, we have some sort of storage. Let's jump into that. So the background of jam was in sort of realizing that these 5 points are what blockchain is about, right? And what sort of Web3 is about in some sense, but certainly what Web3 blockchains are about. And the first one is, resilience is really the thing that is crucial. It's something that Bitcoin demonstrated blockchains could do well. They didn't really do generality or performance back in 2008. Coherency is an interesting one. Coherency is the ability for the different accounts or elements of state to interact with each other, right? And the more easy or the more uniform this ability to interact with each other, and generally the faster they can interact with each other, the more coherent. If some bits can interact with each other faster or more easily than other bits, the system loses coherency, we might say. Yeah. And incoherency is where the state of one bit of the system is assuming that the state of another bit of the system has already moved on, when in fact, at least from some viewers' perspectives, it hasn't. That is then an incoherent system. That's an important point. Yeah. And then we have accessibility, the ability to actually use the thing, basically. Yeah. As a human or some other external service, how easy is it to interact with this thing? Now, Ethereum came along and gave us a bit more generality than Bitcoin had, and Polkadot came along and showed that we could have generality and performance. The one thing that the Polkadot parachain model, however, suffered from was a reduction in coherency. If parachains talk to each other, they do so asynchronously, generally. Technically, they don't have to. It is conceivable that parachains could transition their states in an entangled fashion, coherently, but generally they don't. Generally, if parachains want to talk to each other, they use something like XCM, right? And when the parachain uses XCM, one parachain sends a message and sort of moves forward in some sense. Its state has progressed in some sense. And it takes a little while before another parachain receives it. So for some period of time, one is more advanced than the other. Yeah, it's a little bit like, you know, sending an email or snail mail, a letter through the post. And one person in the conversation is already sort of further ahead in the conversation than the other person. It takes a little while for that person to for them to sort of gain synchroneity again. And that implies a lack of coherency. So let's dig in a little bit. There's my little picture of Ethereum, unscalable. Yeah. Little, small amount of state, all very secured together under the same consensus. Then you get sort of these high performance synchronous networks like Solana, for example, where it's very heavily performance optimized, but it's still basically the same thing going on, right? Everything, all machines on the network have to execute all of the work the network does. And it turns out that if you give it a little bit of thought, this is just not scalable. Yeah. You're going to hit a glass ceiling. Basically, if you're the glass ceiling is how fast can a single machine on the network be expected to go, minus how much time is going to take to send and receive all the information to all the other machines on the network. Yeah, that's your max. That's your limit that you're going to hit. And indeed, it also tends to be fragile and centralized. So other ways of sort of scaling, Cosmos came up with this model where all the different networks secure themselves with their own consensus, but there is some sort of standard for sending messages. Now, as long as each network trusts the other network's consensus to be correct, it's fine. But what happens if there's a nice big network of networks and then one of them fails? One of them ends up with a bad validator set. Well, you have this concept of causality poisoning, basically, because they have a cause and effect relationship. Because when one says, oh, some USD has been burnt here, mint it on the other chain, and the other chain just trusts that state transition, then if one of them breaks, it sort of, to some extent, depends a little on the detail, breaks the other networks. And this isn't desirable. And this is why it's stated as insecure. But there's also another interesting point, which is that there is this persistent state partitioning. These networks are independent and they're separate. If you want to store some balance or some data or some state, maybe some identity information, you have to choose where. Yeah. And if it's on one, it's not on another. Yeah. Because when you update it, you don't want to have to update it everywhere. You want to update it in one place. And this then becomes an issue because you have to choose ahead of time where you're going to put all your stuff. And presumably, if you put it in the yellow one, your stuff, your identity information, it's going to be easy to get at from other stuff in the yellow one, but not so easy to get at from stuff in the blue one because it's farther away. It's on a different network. Yeah. And therefore, we call this a state partition because we have effectively partitioned the overall state of the system into separate networks. And we call it a persistent state partition because once you've made your choice about which network your application is deployed into, it's really hard to change it. So Ethereum, this is a little out of date. Ethereum has switched their mind again, but that happened this year. But up until not so many months ago, this was the declared Ethereum plan. These days, it looks a lot more like Nia and Polkadot, what it's worth. But in those days, it looked like Cosmos, but with basically some extra security gubbins. The issue is, the main issue that I've highlighted here is the same as with Cosmos. There's persistent state partitioning. It's also a bit patchy, right? This idea of lots of different L2s. I'm not going to go into what an L2 is. If you don't know, don't worry about it. And then this is the sort of Polkadot 1 drawing. Now, you can see the nice thing about this is that the dotted line, the sort of consensus boundary, sits around all of the networks, which makes it secure. This is a good thing. But we still have the issue of persistent state partitioning. You have to choose which parachain your application gets deployed onto. And if you deploy it on one, it's going to be easier to interact with the other things in that parachain than it will be to interact with the things in other parachains. Yeah. So why do we do the persistent partitioning? Why not just stick everything in one big pot, one big crucible? This is an interesting point of note, almost a philosophical one. In fact, I would argue it really is a philosophical one. I call it variously the size synchrony antagonism or the size coherence antagonism. I mean the same thing by it, really. Basically, if you have a system, any system in this that is bounded by the philosophical limits of this world, right, of this universe, yeah, speed of light, right, that sort of thing. If you have any system and you want it to do some sort of compute, some sort of state transition, right? And I mean this in a very broad-minded sense. So I include like physical systems, yeah, I include biological systems, I include chemical systems, I include microchips, right? I include people, social systems. Doesn't really matter what the little bits that are doing the compute are. But what we're saying is we have several bits that make up a system, probably several million or billion or trillion, right? And they interact with each other in some way, presumably some controlled way if we expect to get useful work out. Well, if we want to work with more data and do more compute, yeah, if we want to calculate more stuff, then it follows we should add more state, more individual bits, whether they're molecules, transistors, humans, biological structures, biochemical structures, into this overall state, into this overall machine, this overall system. Now that implies one of two things. Either it gets denser, and we'll assume for now we can't just make it arbitrarily dense, because to make it denser would imply better technology. This is something that we are slowly getting better and better at on the silicon front, yeah? We make our microchips denser and denser and denser. But at any particular time in history, there has been a limit to that density. It has increased over time, but there is always a limit. There's a limit today. So we assume that we can't make it denser, at least not just because we want to add more things and not without appropriate time and research. So what do we do if we can't make it denser? Well, we make it bigger. All right, easy. Now, think about all of the distances between these elements of our system. People, if you want to imagine a human organization, human computer. Biochemical elements, if you want to imagine a cell. The brain. Transistors, if you want to imagine a microchip. Molecules, or even atoms, if you want to imagine just a pure atomic or molecular computer. Doesn't really matter what. They're going to be, on average, the distances are going to be bigger. Yep. Because the machine is bigger and it's full of these components, of these state atoms. Yeah? So the state atoms, on average, have to be farther away from each other. Yeah? As the machine gets bigger, the distance between the components that make up the machine must, on average, increase. There's another repercussion as well. The variance of distances will also increase. For any given pair of state components, there will be a greater range of distances they might have. If we take a pair at random, they might still have a very, very, very small distance, whatever the limit of the density is, right? The smallest distance that we can support, that our technology can support. But they could also be at opposite ends of the machine, of the system, yeah? So as the system grows, that variance necessarily grows. So the average grows and the variance grows. Basically, our bell curve just increases, gets wider and wider and wider, and farther up the of the x-axis. Now we know that there is a physical limit to how fast causality can take effect. This is called the speed of light. Yeah? Heard of the speed of light? Yeah? It's a physical constant. Anyone know what it is? Go on. This is the fastest that two different bits of our universe, of the physical world, can interact with each other. So if they are, for example, if two elements are 1 light year away from each other, it will take at least a year for anything that happens on one element to affect the other. It might take longer. It might bump into things on the way. Yeah. The speed of light is actually the speed of light, or at least the number quoted is the speed of light in a vacuum, right? If there's nothing to bump into, there's nothing that's pushing it back or anything like that. So we know that there is a limit to how fast things can interact at whatever distance. We know that as things are farther away from each other, even in perfect conditions, they will take longer to interact. What does this mean for our coherence or our synchrony? Well, it means that as the system grows and the variance and the mean of the distances increase, the system has to proceed more slowly, right? Assuming that we want everything, all state to be resolved at the same time, then we have to move only as fast as the furthest elements themselves can keep synchronized, can keep in the same state. This is actually an interesting limit that the universe has presented us for computation. And it's not one that's widely talked about, but I find it a very interesting one. Now, there's a second interesting point to this. And it's to do with the fact that the variance increases. The variance increases. So the mean increases, okay, so if we want everything to stay totally resolved at all times, we simply have to go slower, right? But if we relax that and we just say, well, stuff that's local to each other, we want that resolved at all times. But stuff that's a bit farther away, we're not so bothered that they are resolved. Well, the fact that the variance increases implies that we can move faster than we should. We can still move on a local level about as fast as that small system could possibly go, which is to say, basically, the time it would take for light to travel between its corners, its opposite corners, its diagonal. But that leads to an issue with synchrony. How do we manage the resolution of the system as a whole if these small pockets are sort of moving faster than it could possibly take for information to travel out from the pockets and actually resolve the wider state? Now, we're nowhere close at the blockchain to hitting these physical limits, but the principle is the same. We still have our little speed of light. It's not the speed of light. It's all sorts of, there's all sorts of factors involved in this: network switching speed, CPU, memory access speed, right? There's a lot of speed limits that we have to, that we are bound by, but it's the same principle. As we increase the state of the system, we have to either just go slower or split it up and then figure out how to resolve it later. Polkadot provided one model, and it's a similar model to the Ethereum, NEAR, and Cosmos models, which is to say, basically partition it all. And it's an old model at that, right? If you look at databases, they'll do something similar. They'll basically take tables and split them up, and then store them in different computers. And as long as you want to, as long as your query only affects one shard, right? Then it'll be fast. It'll be as fast as if it were all just stored on one computer. But if it involves multiple shards, and particularly if it involves cross-referencing across multiple shards, then it'll be a lot slower. Yeah, because of the speed of light. I mean, ultimately. So that's the reason we want to grow these systems, and we still want them to go fast. It's unacceptable for us to grow a system 1000x and then for it to go 1000 times slower. Yeah. So let's get a bit more visual. This is our desired system. It's a state machine, and it has a bunch of processes, or smart contracts, if you like, smart contract instances. And they don't stop, right? They just keep going, like a process on your computer. Yeah, you fire up, I don't know, Notepad. It doesn't stop every 6 seconds and then tell you to, at the end of the 6 seconds, please save all of your document. It's closing now. And then get you to reopen it for the next 6 seconds and reload the document, do your bit of work, save the document, close, reopen. No, that would be ludicrous. Although to be fair, actually in the old days, you did turn your computer off quite a lot. But these days, no, we have suspend and resume. So what did we get with Ethereum 1? Well, we got this, which isn't much to compare with, is it? So we got like this single-threaded smart contract. I drew them in blue because they don't really have proper memory access. It's really sort of idiosyncratic memory accesses. Nothing that you would be able to really compile regular software to target. And then there was a big long period where, quote unquote, the computer is off, right? It's just not doing any work for that, I don't know, whatever, 15-second cycle. And then it kicks off again, right? And we get a bit more work done. That's the sort of compute model that we got there. Now, I hope you can see this is just a simplification. If you only have like one compute thread, then it's equivalent just to take all 4 of those arrows and just stick one there, right? You just have a bigger state, basically. Because each of those little state machines, those little processes, will have their own state, right? Well, you can just do the classic trick that, Alan Turing did when he proved that his Turing machine was equal to, as powerful as any computer at the time. You can just basically say, we'll make a bigger program And as long as it only actually has one CPU, it's fine just to use one arrow and pretend that that arrow, it just happens to be an amalgamation of all of the, that arrow just happens to be running software, which is an amalgamation of the 4 arrows software. And, you know, as some of the competitors sort of did a bit of development, did some optimizations, cut a few corners, they got something more akin to this. Thicker arrows, maybe they used a couple CPUs, a couple of the cores of the CPUs rather than just one. I think that's what Solana does, sort of parallelizes a bit over a single machine. Still, machines have to do all work, remember. And you end up with these arrows. Bigger arrows, less time wasted, but still single arrows. Cosmos, separate systems, insecure bridging at the top, each with their own arrows, but at least we have multiple arrows now. Polkadot 1, a lot of mad dots, I know. That's just demonstrating the sort of XCM pathways, right? The XCMP messaging. But the point is that there is a big, thick border around. Same consensus, right? And lots of arrows can do lots of compute. But these bars, these vertical bars, demonstrating that the different arrows operate in different state. Yeah? They can't affect each other except by the dot, these dots, these messaging pathways. That's the problem. And the arrows don't go from top to bottom. Remember in the first diagram, they went top to bottom. These ones are still, like the others, stopping halfway. All right, so what's jam? Well, this is a sort of diagram of jam. It's a little, it's sophisticated. It's sophisticated. On the left side, we have this pretty familiar state machine, right? Blue arrows, one at a time. Architecturally speaking, for what it's worth, they don't necessarily have to go one at a time, but that's an optimization for later. Now, the interesting thing, though, is that these blue arrows are not just plopped there on their own. They have other lines feeding them. And where are these other lines coming from? Well, they're coming from this other set of arrows in the middle. And you'll notice that this other set of arrows, they don't have state around them. They don't have one of these thick boxes around them. Why? Well, because they're stateless. They don't have state. Not really, anyway. But they do have a massive data lake that they can draw information from and put information back into. And I'll come to the limits of that and why that doesn't really count as state. Because it doesn't really count as state. But it does help. And what we call this is, I call this a reactor chain. Why? Well, because think chemistry. Yeah. If you want to like react two chemicals together, you'll generally have a place to do it, right? A test tube or some sort of jar. Yeah. Well, that's the purpose of this thing on the right. It's to sort of react these different result data together, because they can't react here because there's no conduit. There's no pathway to react there, right? So that's why I call it a reactor chain. And I call these sideband shared memory coprocessors. Why shared memory? Well, because they all can draw from and output into the same data lake. And they're sideband because they're just sat on the side. Sideband coprocessor. Right, now, so I've been banging on about coherence. How does jam fit in? Well, jam is generally coherent, but with transient decoherence. Now, this is very different to the persistent partition model. The persistent partition model is just fundamentally incoherent, unless you take very particular, unless you limit yourself in certain other ways, right? There's a bit of small print there, but as it's used, practically speaking, in every chain that you're going to come across, it is incoherent. The different partitions operate independently, right? They have an independent state. Changing a bit of state in one of them never fundamentally affects cause effect some change in another, right? That doesn't happen. They are independent machines. There are generally ways that you can change state in one of them and elicit some later effect, but it's not synchronous. Jam is a generally coherent state machine. It never goes out of coherence per se, but that input is stateless. And that's how it manages to get away with this. There is essentially some part of the computation pipeline that's allowed to be not yet committed, if you like. When it eventually is committed, it will be fully coherent. And we never commit unless it is going to be coherent. This is different to the persistent partition model, where each of the parachains commits as the information comes to pass, as the compute is done. And then there's some sort of, one would presume anyway, some sort of consolidation between the parachains. Maybe they have to send a message off to say, hey, by the way, this thing has happened. And then if there's a problem, because say the other parachain says, oh, but hold on, I can't manage that because in the meantime, some other thing happened over here. That can't happen with jam. Yeah. Because nothing gets committed until everything gets committed. Now, it has, because of this, two differing compute environments. It has one compute environment that is, if you like, the stateless one, right? The one that is happening in the middle in that diagram. This one. And we call this in core. Just because these gray arrows are called cores. So in core. And this is stateless, but it does have access to the data lake. And then separately, we have our synchronous, fully coherent, stateful computation environment, which here, somewhat unhelpfully, we're explaining to other blockchain ecosystems anyway, is called on-chain. But we can just call it synchronous, that's fine. And this is stateful. Our data lake is very big by blockchain standards at 1.5 petabytes. You can store a lot of information in that. And it has a 6-second synchronization latency when cores are, in essence, communicating through it. So if one core throws data in there and another core tries to read that data out, then it will take 6 seconds before that data will be available. Sometimes more. Sometimes it might even be 7 seconds or 8 seconds. But we target 6. It doesn't actually matter from a correctness perspective. That's the nice thing about this. And that's one of the attributes of the data lake. Because it's not actually a properly stateful data lake, it's actually just a hash pre-image. No, not even. It's just a cryptographic library, if you like. Anyway, I'll get into that in a second. That's the intercore synchronization latency. If it's the same core, so if some bit of computation comes along and throws something into the data lake from one particular core and another thing later, immediately afterwards, tries to look it up from that very same core, it's instant. So this is a little bit like CPU caching, right? If a process is executing on a particular CPU and it throws some stuff into main memory, on a particular CPU core, I should say, and it throws some stuff into main memory, and then it tries to read it back, it will be instant. But if some process on another core tries to read it back, it will take some time. Why? Well, because you've got cache stuff, right? And it takes ages for, comparatively ages, for the data to get from L1 cache to through to L2, L3 into main memory, synchronized between the CPU cores and then back down again and into the CPU core that wants to read it, right? Now it's all transparent, and you probably wouldn't know this unless you know a bit about CPU microarchitecture, but behind the scenes, that's basically what's happening. It takes longer. Our distributed decentralized data lake, or just the data lake for short, allows us data lookup. As I say, think about it as a library where the books all have a particular index. You know, like libraries work. I mean, actually, maybe I haven't been to a library recently. They're kind of old school now, aren't they? But, like, you know, in the old days anyway, when people did go to libraries, the books would have a sort of little card, right? And the card, they'd have a reference number. It'd be like, I don't know, a 6, 7, 8-digit alphanumeric thing usually. And then when you were looking up what book you wanted, you would go to a really big card index thing that would have all the cards for all the different subjects that you might want to know, and then, you know, alphabetized by author or whatever. And then you'd find the card that you wanted and look up what the index was, and then that would tell you where in the library to go, and then you'd find the book and it would be something TK212, right? And you go there and you go along the, you know, T, whatever, TG, TH, TK, right? TK 90, TK 105, TK212. Bam, there's my book. Right, same thing, except the books are all 4K. Right? So you can think of it as a sort of library with cryptographic indices and 4K books. And the lookup mechanism is optimizable on a network basis, on a decentralized network basis. What does this imply? Well, it implies that you can't choose your key. That's the main thing. You can't choose your key. The key is determined by the library. So if you want to have your book be called GAV 4.2, then tough, you can't, right? This means you can't engineer collisions. Yeah. It also means that it's impossible for two different processes to both think different data, their data, is at one particular index. Yeah. When you put data in, you get an index back. And you need that index to get that data in the future. This solves a lot of synchronization problems, or at least sidesteps them, doesn't really solve them. It's just a different type of facility. All right, don't think we need to do that. Right, so what technologies do we use in Jam? The first one is what I've called cynical rollups. A lot of people don't like this term. Tough, I like it. Elves. Could also call them perfect rollups, I suppose. It's another possibility. But anyway, they are this basically very secure, fast way of compressing compute correctness. Right? You can imagine blockchains are a system of engineering, manufacturing compute correctness. Yeah. Why do you trust a Bitcoin Lite client to tell you what your account balance is? Well, because you can see for yourself, I mean, principle, through the code, through the data, the database, that other non-aligned individuals have put their weight behind the correctness of this information. Yeah. Bitcoin, the Bitcoin blockchain, is essentially, through its game theoretic foundation, a means of manufacturing compute correctness. This is something that has not hitherto, or had not hitherto, been commoditized. Compute correctness, if you wanted it done at, like, you know, a level that would be more or less akin to yourself, you just had to do it yourself. Yeah, up until this point. You can argue maybe cloud, but I'm not sure even if cloud compute is at the level that that those who really care about the correctness of their compute would trust. Elves doesn't manufacture compute correctness. Rather, it extends and projects compute correctness, scales it up. Safrole, actually, and the elves we use for what it's worth, is slightly different to the elves that Polkadot One uses. There's a slight simplification, but on almost all points, it's the same. Safrole is a simplified version of Sassafras, which is a newer parachains block authoring protocol using a ZK-based lottery system, basically handing out lottery tickets that are anonymous and allowing the claimant to show themselves or show their identity only at the time that they actually claim the ticket. And because it's a sort of lottery system, we can actually hand out effectively tickets for each block within any given era, any given time span. And this means that there's only going to be one winner. We can engineer it so there's only one winner per time slot. This is very helpful, and it's not something that some of the, well, our older default parachain block authoring system, Babe, had. Babe, unfortunately, would quite often have two competing validators, block authors for a block. Sometimes even three or even four, right? And this led to forking, which is forking annoying. We have, in addition, Grandpa. This is unchanged from Polkadot, and this gives us our finality mechanism. And the PVM. This is a newfangled bit of technology that actually has a few different facets, but overall, its point is to provide an optimum computation substrate for the system. Whether that substrate is used to operate smart contracts, or pallets, or blockchain state transition logic, or stuff that sits at the sort of even sort of higher level, lower level jam services. All of it runs expressed in PVM, and I'll go on to talk about PVM now. So I don't know if you're familiar with it, but RISC-V has recently gained a bit of fame. It's been declared by the Chinese government to be part of their long-term roadmap for gaining some independence for their hardware efforts. They don't want to be so dependent on Intel and AMD and all the rest of it. It is a open source instruction set architecture. It's modular. And it's got some sort of parameterization, some configuration options, which make it pretty handy tool to use in a variety of situations, from small embedded systems all the way up to big fat servers. PVM is based upon RISC-V. It's not RISC-V exactly, but it's not far off. We've made some optimizations ourselves, and it's based on one particular sort of configuration, if you like, or parameterization of RISC-V, along with one or two, I think two actually now, sort of extra modules. Because it's based on RISC-V and it's relatively close still, RISC-V code can be recompiled into PVM quite easily. We have and maintain a PVM recompiler that takes RISC-V code and translates it. And this is part of our broader sort of compiler suite that allows us to compile stuff like Rust code into PVM pretty much directly. Now, PVM has 13 usable 64-bit registers. 2 of them are reserved for operating system use and therefore aren't used by the compiler. One of them is the 0 register, it's always 0. And it also has a very obvious, simple memory system, 32-bit address space, 4 kilobyte pages. Oh, 4 kilobytes, same as the Jam DA. Harvard architecture. So it means, if you're not familiar with this, that its program code isn't stored in main memory, stored off to the side in a sort of ROM, yeah, that's separately addressable. Or, yeah, I think actually it's not addressable at all. Now we get to the interesting stuff. It can be recompiled, PVM, using a streaming secure recompiler, order n, order size of the program, into x64 code. That's hardware that servers will typically use. And although we haven't actually prototyped it yet, expectations is that it can be, same techniques can be used to get it into ARM64 as well. But for now, we focus on server. And it can be dynamically metered with actually a minimal overhead. Now, this comes with some, well, one very important caveat, but the actual metering, so adding the extra or maintaining an extra sort of counter as to how many instructions have passed, that doesn't cost very much. I'll go on and talk about why that's only half of the problem. Its stack, like with regular computers, sits in main memory. If you snapshot main memory and the registers and the program counter, and then you kick off the machine again at some later stage, having restored main memory, or at least the addressable pages of it, and the registers, and the instruction counter, the program counter, then it'll just carry on going. It'll be like nothing ever happened. Yeah, this is different to some other comparable systems like WebAssembly, where the stack is a separate data structure and it's pretty opaque. That isn't very helpful to us when we want to do continuations. And our experiments suggest that if this thing runs flat out, we can get it almost about half as fast as native, or our benchmarking code anyway. Now, I mentioned before, this 10% metering overhead is only half of the story. I'm going to come back to that in a second. Right. Excuse me a second. Oh. Can we connect? Yes. Yeah. Good. So, shared state is arranged into services. Services are the the sort of top level thing that Jam deals with protocol-wise, right? Services are a little bit like smart contracts. They have two entry points. It's a single piece of code, but just two ways in. Yeah. The first one is refine, and that's the bit that runs statelessly and can read and write from that, or pull books out of and throw books into the library, right? The DA. And then its output makes its way into accumulate. And once it goes through accumulate. That's effectively a commitment into the state, the final big state of the system. Until it gets to accumulate, so while it's just in refine, the system just doesn't know anything about it. Yeah. If for some reason it got lost on the way, no bad thing had happened. It would be like kind of getting halfway through a MySQL atomic, writing a MySQL atomic database operation, and then, you know, the server goes off, and when you turn it back on, it's, you know, it just reverts back to the beginning because it's atomic. Yeah. Basically, what's going on here. So accumulate, you can almost think of as commit. Yeah. And as I say, it's like a smart contract, but the computation is a lot more sophisticated. So firstly, it's staged. You've got your refine and then you accumulate. 2 stages. Right? Normally in a smart contract, it's only 1 stage. Secondly, it's pipelined. Refine from time t+1 happens at the same time as accumulate from time t. Yeah. Usual classic pipelining. It's also distributed. At time t, we might have 10 different refines happening for our service, all producing some sort of output, some sort of like commit code. And it's up to accumulate at time t+1 to figure out how to amalgamate all of that together. Yeah, that's accumulate's job. So stage, pipeline, distributed. Rather than having some like per transaction payment, which wouldn't really make sense when, you know, firstly, we don't have any transactions, and secondly, if we did, there'd be so many of them that we'd probably end up spending a lot of time trying to, you know, take individual payments. So we skip all of that complexity and just say we sell this stuff on bulk, right? You buy at least 1 block's worth of compute, and maybe a lot more, maybe a month's worth. Yeah. But when I say 1 block's worth, I don't mean like the whole jam block, because that's even more blocks worth, because there's so many cores. I mean 1 core, right? But you can process easily a block's worth of compute in a core, in 1 time slot of a core. And these things are generally asynchronous. So when they interact with each other, they do so asynchronously, not synchronously. Most smart contract networks, like Ethereum, they support synchronous composition. We don't support synchronous composition between services. Now, Jam is permissionless, which means you can add new services without any permission, without any special privilege. And the service, all of its code and data sit on chain. There's no great limits placed on services beyond those required to stop, you know, people griefing the chain. And we could imagine a service, an example service might be like Parachain's service, right? That basically just does Polkadot1, just the whole Polkadot1. That would be an example service. But we can imagine lots of other services as well. Jam isn't opinionated with regards to any of this higher level stuff. Jam is really compute machinery. Right, so let's talk a little bit about the pipeline. Now, I mentioned refine, which happens in core, and accumulate, which happens on chain already. And that's the service code. Service code has refine, has accumulate. In addition, there is authorizer code. Authorizer is an extra little bit of code, not big, very small, doesn't take long to execute, but it sits at the very beginning and just makes sure that the work we're about to do has been sort of paid for, if you like, is authorized. Yeah. Because we don't take payment up front, we need something up here that sort of guards against just random people coming along and throwing, whatever compute that they want to do. And us doing it. So it's essentially a gateway. So we come in on the authorize with our work package. That's a little box. And our authorization. And then we end up with a bunch of work that we want to do and some trace from that authorizer. What's a trace? Basically, it's a little piece of information that describes why we authorized it. Typically, this will be an account ID, right? Typically, this will be the person that signed the thing that had paid for the time on Jam, typically. But we leave it to the authorizer code to sort of denote the meaning for its output. We don't care, but it will get passed in to the service code. That's the important thing. So the service, if it knows about what authorizers are and do, it can interpret this appropriately. Maybe it doesn't care, but it might care. And if it does care, it has the option of introspecting. This workbook goes into refine, which does all of the hard, heavy lifting. Massive amounts of data, it can fetch from the data lake, lots and lots of compute. And out of here, we get a digest, which you can think of as a sort of commit log, right? The stuff that needs to be committed, having done, processed all of this work. Call it a digest. And if we happen to do lots of refines for the same service, we'll have several of these digests, each with their own trace, assuming they're coming from different work packages. They then get fed all at the same time into that services accumulate. All at the same time. That is a trick that we do, because oftentimes I'll get asked, how do you manage MEV? How do you manage the possibility that we have lots of transactions all coming in, all being processed at the same time? How do you decide what order to do them in? How do you decide what order to process these refine outputs in? And the answer is very simple. We don't. We leave that to the service author. We just give them all of their information at the same time. Yeah, they can see all of these at the same time. And they have to choose what order to do things in. And it might just be an arbitrary order. It might just be the first one The one of index 0, they process first, and the one of index 1, they process second. But they could also see, right, I've got 2,000 transactions to process. I will fire up a random number generator, shuffle, right, and then process in that shuffled order. Right, I'm going to start with 1,103. Now I'm going to jump to 579. Yeah, da 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 da. Doesn't really matter, but it doesn't really matter to Jam. It's up to the service author. We leave it entirely at their discretion because they know. How are we to know what order things should happen in? We're just a compute machine. That's up to them. Now you also see there's an arrow going back into accumulate. This is because sometimes in accumulate, you want to interact with other services. You want to sort of fire off a message and have another service receive it. Or you want to process a message coming from another service. Well, that also happens in accumulate. It has to. It can't happen in refine because, as I said before, refine is stateless. So it has to happen in accumulate. There's no other place for it to go. Yeah? So accumulate ends up processing not merely the outputs from refine, these digests, but also any messages or memos, we call them, because they're only little short messages, I think 128 bytes. Memos coming from other services. And other services, when they send a memo, they can also send sort of cash with it. They can send tokens with it. Yeah, so this is this functions as a very low-level clearinghouse as well. It tends to be quite helpful to have a low-level clearinghouse. Good. I think I covered all of this. Yes. Now, I'm not going to go into that. What time are we on? 10 nearly. All right. Fine. Right. Let's talk a little bit about refine. Yeah. So refine is performed on a single work item. I put it there as a little book emoji because it's quite a big bit of data that we're talking about. These workbooks that are fed into refine max 12 megabytes, right? We're not talking about some tiny little transaction here. We're talking about a pretty serious chunk of data. Now that 12 megabytes includes any new information into Jam and anything to be fetched from the data lake. It's a sort of amalgam, right? If you use more of one, you have to use less of the other. You can have just 12 megabytes of totally new information and nothing from the data lake. You can have no totally new information and 12 megabytes from the data lake, or you can mix and match. These items in their refinement may also place 12 megabytes back into the data lake, like introduce 12 megabytes more books into that shared library. They can execute for about 5 seconds of PBA. Probably that's actually going to go down. I'm going to change that now. So probably more like 2 of PVM gas. For what it's worth, the reduction here is due to the complexities of modern CPUs and the inability to come up with a gas model that properly reflects their compute speed. But I will go into that as a later topic in a few minutes. And these items can yield up to about 48 kilobytes of output that get fed on into accumulate, right? That's the digest. During their execution of refinement, they can do a few different things. So they get a few different bits of input. They get this trace, which is the output of the authorization. They obviously get the data itself. They can look at other items in the same work package. This can be very helpful for a thing called co-scheduling or co-sequencing, to know what else is going on at the same time. Now, they can't look at everything that's going on in Jam at the same time, but they can look at other things that are scheduled at the same time in their core. And that can be very helpful. Now, the other thing that is particularly helpful here is that they can invoke new instances of the PVM, right? They can make a whole new instance of a virtual machine, initialize it however they choose, and then kick it off. Because they can initialize it however they choose, they can do the trick that I mentioned 5-10 minutes ago about with continuations. If they know what a previously invoked machine's end RAM state was, and registers were, and program counter, then they can continue from where that machine stopped, effectively providing continuous compute or a continuous compute environment. We'll come to this in a second. In accumulate, as I said before, it's performed on one or more digests of a service, as well as memos, actually. Not just one. When you get accumulate called in your service, you can have many outputs from refine, many digests, and also many memos coming in. Or you can inspect all the traces to understand how the digests arrived, who authorized them, why. And per digest, you get about 10 milliseconds worth of PVM gas, probably a bit less. But you can do a lot in 10 milliseconds on PVM. You get more if there's memos as well, right? So memos come with their own PVM allocation, gas allocation. And this is where you can do all the stuff, like all the inter-service stuff, transferring funds, sending memos, that sort of thing, reading other services state, all of the stuff that you would expect in a coherent system. This is the slight caveat. When you transfer, it's asynchronous, right? It doesn't happen immediately. So basically it's queued up, and then at sort of the next processing batch, the service you're transferring to will receive it. Foreign state, when you read foreign state, so when you read some other services state, that is, you're going to read what it was at the beginning of your execution, right? So if it happens to be sort of conceptually executing at the same time, you're not going to see any of those changes. You'll always see what it was at the beginning of your execution. Yeah. Not going to go too much into that. Right, now, I'm going to jump back a little bit. In fact, no, we're not. I'm going to skip this for a second. Right. So, core VM. So that's Jam. Now, I'm going to break for coffee in 10 minutes, but first I want to talk a little bit about core VM. Now, you can think of Jam as decentralized silicon, right? In essence, it's it's a server, right? It's a 341 core server with some memory that has a slightly sort of mad addressing system, right? 1.6 petabytes of it. And if you imagine that as jam, you're not going to go too far wrong. That's more or less what it's doing. It's just doing it through a decentralized network of 1,023 less capable computers, right? But just because we have like some silicon, like server hardware, doesn't mean that it's especially usable. There's software that you need that needs to be on the server hardware before you're going to be able to write any applications for it at all, right? There's firmware. When you turn the thing on, you need some sort of firmware, BIOS, whatever, that kicks in and initializes all the hardware, checks everything out, loads an operating system. Yeah, that's one thing. But you also need an operating system, something that can handle processes, scheduling, privileges, inter-process communication. Yeah, managing data access, putting it into a sensible format so that rather than having to fiddle about with interrupts, you get a file system. Yeah? Who wants to fiddle around with interrupts trying to figure out how to get data blocks into an SATA or SSD or NVMe? Yeah, this is nothing that anyone here would want to be doing, I trust. No, we like our hard disk drivers and we like our file systems. Well, this software needs to exist, similar software, corresponding software for jam. Before we jump into Core VM, let's look at jam's tools. So one of the things that we have for jam is a test net. It basically just sets up a 6-node, 2-core local test net. Now, normally on blockchains with local test nets, you'll usually just have one node, right? Because they're basically single-threaded, most of them. We can't really do that with jam because it sort of fundamentally needs more than one node in order to give its in some sense, give it sort of its API, its interface. It doesn't really make sense. I mean, I guess we could just about have a one node, one core thing, but it doesn't really make that much sense. 2-core is probably the least that makes sense. And for 2-core, assuming that we have 3 nodes per core, and it would take quite a lot of fiddling around with a protocol spec to change it, then we need 6 nodes. So we have a little executable that spins up 6 nodes and gives us this sort of mini jam, 2-core jam. Big jam is 341, that's Polkadot. That's what's coming to Polkadot. Small jam is 32, that's what's going to Kusama, it looks like. Yeah, but really small jam, like runs on my laptop jam, that's 2 or 6 node. We also have jam top. You're probably familiar with top, like shows you all the processes running on your machine. Table of processes stands for. Well, we have jam top. This shows you all the processes running on jam. Yeah, you got like video tests and Core VM, and it tells you all of the things to do with the services. It basically gives you an overview of your jam server. We have a tool, Jam T, that basically lets you interact with jam and with some of the very central pieces of software that we have that run on jam. In particular, the bootstrap service, which you can think of basically as a BIOS for Jam. In this little example here, Jam T has been kicked off, and we're just making a new VM and sticking the video test code into it, along with an initialization for how much gas, I think it's by default, will author blocks with. That's right. And you can see it's doing its various things. Finally giving us a service ID that is this new, that is the address of this new VM. So let's think a little bit in terms of architecting for Jam. Two areas that we've put code: refine and accumulate. In refine and accumulate, both the correctness and the code are guaranteed to be what you expect, right? They're both guaranteed to be correct. The code is guaranteed to run correctly, and it's guaranteed to be the right code. But in refine, we cannot inspect the storage of a service. In accumulate, we can. In refine, all inputs are provided by whoever is building the work package. And it's up to the refine code to check that those inputs are the ones it wants. Of course, it can't check the data, but it can check what the data represents, like the address, if you like. And we can inspect the builder, their identity, who they are, via the authorizer. For the builder, or for the work package that the builder built to get through into refine, it needs to have an authorization. I mentioned that before. I skipped over precisely how the authorization works. That's detail that I don't think is needed yet. But the builder is inspectable via this trace we get from the authorizer. In accumulate, the inputs are not provided by the builder, but rather they're guaranteed to be the output of refine or a memo coming from some other accumulate code, right? So all input to accumulate is sort of guaranteed to be the correct output of some other compute in the system. The only input here that sort of can come from the public, so to speak, is this one, the ones that are provided by the builder. And the builder, if you like, is the sort of transaction collator. It could even be the sort of transaction creator. But that's where the arbitrary sort of information from the external world can be selected. So in essence, the builder of these work packages, these things that are fed into refine, they can, in essence, oracleize storage as supposition, and it's up to refine and then accumulate to check that those suppositions are correct. Because refine can't inspect storage itself, if we need information in refine from storage, the best we can do is have the builder hint it to us. We can't trust the builder. We can have them hint it to us, and then we can work on the assumption the hint is correct, pass the hint in with our sort of commit log, if you like, and then before we commit it in accumulate, where we do have access to the storage, we check the hint. The hint is bad, we don't commit, and we punish the builder. Yeah, that is the model that we have to employ. Why do we have to employ it? Well, the speed of light. Yeah. We cannot expect to read all state from everywhere at the same time. Doesn't work. Speed of light. So we have to employ certain tricks. What about splitting between service storage and the data lake? So these are two different things, remember. The data lake is this sort of mad, huge 1.5 petabyte library of books that are exactly 4K big, indexed according to our resident librarian. You can't choose your index when you put a book in. And the service storage is just a regular key value, right? Keys happen to be 32 bytes. But beyond that, you can put what you want in there, as long as you pay for it. You can choose your own key. But it's namespaced on the service, right? So a service can't chuck data into some other service's storage. That wouldn't make any sense. So how do we sort of imagine this split? Well, firstly, the data lake is accessible in refine, but not in accumulate, right? Only in refine. Service storage is only accessible in accumulate. So two different data resources for the two different stages of the pipeline. Data lakes not nameable, right? The identifiers are cryptographic. They're not strictly content-based. They're effectively indices into a Merkle commitment, or what it's worth. Whereas in service storage, it's namespace under the service, and you give it whatever names you want. The data lake has very high throughput. Over JAM, it's 2/3 of a gigabyte a second. It's a lot of data throughput. Whereas service storage has comparatively low throughput, about an order of magnitude less. So what do you do when you're writing JAM services? Well, you want to get as much reading and writing of data into refine as possible. Yeah, it's got the big bandwidth, it's got the big storage. You pass your references into accumulate, and it's the references that you will tend to store in service storage. Yeah. And actually, you only use service storage to track the overall state of your service, not the individual data. Yeah. You care more about when we talk about what service storage is used for, you're really storing a digest of your service's state, not the state itself. Yeah. And when I say digest, I don't mean the digest from the terminological digest from before. What I mean is you're storing effectively it's compressed, right? You're not storing the data itself. You're storing a commitment to the data, or you're storing a commitment to the data. Yeah. Wheels upon wheels. Why? Well, because you might have a huge amount of data. JAM can support services that have gigabytes of data. Even if you only store 32 bytes for every 4K of a gigabyte, you'll still end up running out of bandwidth in your service storage, in and out of your service storage. So in this case, you would need to Merkleize it further. But point is, you need to do your actual data crunching in Refine using the data lake for any major service you're going to build, and only stick commitments in your service storage. So Core VM. Core VM is basically a pre-packaged operating system for Jam. You can think of it, if you like, as Docker for Jam, right? I don't know if you're familiar with Docker. It's a sort of container system that pretends to be Linux. You can stick some executable or whatever, bunch of executables and libraries and whatnot in there, and then run it on any computer, and it'll all just work because the computer takes the responsibility of making it look like Linux, like a vanilla Linux. So that's Docker for Jam. Core VM effectively gives you this, not Linux, but very standardized, normal looking compute environment. And this is my picture of it. Now, we're starting to look a lot like what it was that I had put at the beginning, right? When I introduced this little format of drawing. We've got one thick box, good. We've got red backgrounds to the arrows, or orange, indicating sensible memory. Good. In this case, 32-bit address space, 4 kilobyte pages. The arrows go all the way from top to bottom, indicating our applications, our services, or our VMs in reality, are not services, Jam services anyway, don't stop every 6 seconds. So far, so good. However, there's a couple of limitations. One of them is we've still got these bars, same bars that we had with Polkadot 1. What does that mean? The service, the core VM instances, right, the different Dockers, run in essence in isolation. Yeah, they can't talk to each other synchronously, not under our core VM operating system. If they want to talk to each other, they can send messages. And as it turns out, these messages, they can stream them, they can be pretty unlimited in terms of size, and they are reasonably fast. So it looks quite a lot like a pretty standard operating system model, right? You can send messages, you don't get the shared memory thing, and otherwise you fire up a process and it just sort of continues, apparently, according to itself anyway, uninterrupted. Of course, the operating system scheduler will know that it is interrupted, yeah, that it's constantly being tasked in and out on a CPU core, but that's not relevant from the perspective of the program itself that's running. As far as it's concerned, it's always running. So Core VM effectively emulates a machine with near x64 speed, RISC-V compatible. So if you can compile to RISC-V, you can compile to target this ISA with page memory, continuous execution, and message passing. It can run regular software. And this is a bit of a breakthrough. There are still some caveats. The most important one is charging for the resources used, and how to do this in a fashion that doesn't impact usability. And that's something that I think some of the early jam practitioners will spend some time thinking about. So how does it work? Well, an initialization, we zero some registers, we zero the program counter, we empty the page table, and we set what the code, the program code is. That happens. So that literally happens on that. Remember I showed you jam tool and that thing VM, new VM, give it the PVM code. Well, that happens as soon as that service gets initialized. Then we advance it. We create work packages which advance the service along. So how do we advance the service along? Well, we advance the PVM. We basically we've created a virtual machine. We advance it. We sort of recreate it from our knowledge of what its registers, program counter, and RAM page table is. We recreate it. We advance it. We tell it, kick it off. Process some instructions. Now, it'll process some instructions, and it'll eventually, one of three things will happen. Actually, one of four things. It could sort of end all by itself, right? Either successfully we have a sort of means of exiting the PVM successfully, or through a panic, right? Unsuccessfully, right? So that's a separate possibility. But assuming it doesn't exit, it will finish advancing with one of three conclusions. Either there's been a page fault, so it's tried to read some memory that it's not addressable. If it's a page fault, we fetch the RAM page from the data lake. And if that RAM page never existed before, we never used it, well, then we just say it's all zeros, and we introduce a zeroed page into our page table. It's easy. And then we carry on, keep advancing more instructions. The page fault will have gone away now because we've told it what the page is at that address. Maybe there's a host call. Maybe it's trying to do something sort of extrinsic to the actual program code. In that case, we actually only have one sort of host call, which is output information, right? We have basically a sort of general output stream from the program. This actually is multiplexed, and from this output stream, we have like audio output driver, video output driver, console output driver, and a bunch of other potential output drivers. So we have like basically a means of yielding data from this PVM instance. And what do we do with it? Well, we timestamp it because it's all in a stream, and we stick it in the data lake. And then we continue. And when it's out of gas, eventually it will run out of gas. We snapshot all of the pages that had changed, and we stick them in the data lake. Now, all of the information that we need to both understand what the machine had done and restart the machine is in the data lake. All we need to know is what these cryptographic references are. Yeah, we need to remember those so that next time we'll have the library tickets to be able to go and get our books to make, to put these pages into RAM as they're needed. So within the data lake storage, we have the RAM page contents, Now we call them the guest RAM because we want to distinguish between the VM instance that is, running whatever it is our program is, and the PVM instance that's running the service. Yeah, we're not talking about the service RAM, we're talking about the guest RAM. And also the output of any streaming virtual devices, such as video frames, audio frames, console frames, and whatever else when the time comes. Now within service storage, and you remember this is the stateful one, this is the coherent one. We want to keep the data minimal, but we have to store everything which must be universally known and coherent, which is to say stored in a single location. So we need a commitment onto the current state of the guest PVM. We need to know exactly what state the PVM actually is in. Because if we don't know that, some malicious builder could come along, pretend that it's in some other state, move it forward into some inconsistent state, and get away with it. We'd never know the difference. So it's crucial that we record and maintain some commitment to the state of the PVM. In this case, we store the registers and the program counter directly, a full page table, which maps the page index to the hash of the page, and also the code hash. We also store time-indexed device commitments, video frame references, audio frame references, and console references. These are references into the data lake, so that someone coming along who wants to look at the video frame from one particular time can find it easily. Now, you might ask, and hold on, and then also we have the bookkeeping, which is just some privilege, right? The account owns it, and this just allows us to update things if we want the owner to, for example, change the program code or reset the memory. Now, you might ask, why are we storing data lake references here, but hashes here? And it would be a very reasonable question. Well, we store the data lake references here. This is the easy one. Because we want to facilitate the extraction of this data from external entities. Yeah. And external entities have no way of looking up a hash preimage generally. If that preimage happens to sit in the data lake. There isn't that facility. But there is a facility of looking up a 4K book using a data lake reference, using one of these library cards. So we make their job easy, and we put the data lake references in here. So why not put the data lake references in here? Well, the data lake only lasts for 28 days. Which means at the end of it, if your data isn't as sort of past this 28-day period, there would be no way of that data lake reference would become meaningless. Yeah? Because it's not content addressed. The data itself, you can't take the data lake reference and the data and somehow derive one from the other. The data lake reference is pretty arbitrary. It's just what the librarian decided at the time, where the librarian in this case happens to be the JAM protocol. Once it falls out of the library, the reference is useless, which means we would have no way of kicking the program off again, because we'd have no way of using this reference and getting data from it. So better that we store the hash. And then you might probably say, well, hold on, if we only have the hash, how do we find the data in the data lake? Well, the answer to that is we assume that the builder is keeping track of things and that they have internally a hash to data lake reference lookup sat in there. And if they don't, that they are capable of looking at previous blocks and deriving it themselves. We could store both, but if we stored both, we would have potentially an issue in bandwidth, or a bigger issue in bandwidth. Storing both would increase the bandwidth requirements by over 2x, and that's undesirable. We'd be able to do a lot less. So we store the hash, we put it in the data lake, and we leave the tracking of hashes to data lake entries the job of the builder. And in reality, the builder will most likely not use the data lake most of the time anyway, because they will already know, because they'll have built the previous instance that moved, the previous work package that moved the PVM along. They'll know what the data is anyway. Good. All right. Quickly go over a couple of the other things before we break for coffee. We have a few other tools. CoreVM Player is a tool just for monitoring these output streams of CoreVM services. So like video, audio, console. Basically, it's a window that represents the output of a CoreVM instance. Yeah. So imagine, you know, the usual thing. It's like if you do a what is it, an RDP, remote desktop protocol. If you do like ever use this? It's like Windows has one. You can basically kind of open a window that is what some other Windows machine would be displaying on its monitor. Yeah, X11 on Unix has similar functionality. Well, if you like, that's this. Yeah, it's a monitor that displays what the CoreVM instance of the guest would be sort of displaying on its monitor if it had a monitor. Yeah, I mean, it's purely virtual, right? Purely decentralized. So it doesn't have, there's no sort of concept of a physical monitor that you could plug into this. But there is a software monitor that you could plug in, and it's basically this. And I think we actually renamed it now. It's not CoreVM Player, it's CoreVM Monitor. We also have CoreVM Builder. This is the thing that builds the work packages. Yeah, this moves the PVM instance along, the guest instance along, moves the service forward. And this does the cunning stuff of understanding what a given CoreVM guest, what RAM pages it needs, fetches them from DA if necessary, and builds the work packages around them. So that when they're executing, they don't need to inadvertently and unpredictably go to the DA, which they can't. They can't go to the data lake unless the work package has sort of said it needs to go to the data lake for these things. Good. That is where I'm going to leave it for now. When we come back in half an hour or so, I'll give a bit of a demo, I hope, fingers crossed, and we will have a Q&A session. Thanks for your attention. Enjoy your coffee.